All right. So now we're all ready. We've set the groundwork. We're all ready to define what we mean by probability. Now, the definition we're going to look at is a practical definition of probability. Probability theory itself is a well-formed mathematical theory. We're not going into that. We are going to try and get a practical definition of it. Just like when you learned geometry, going back to the geometry analogy, you learned about straight lines there. And we know that those only exist in somebody's mind, whereas all around us are all sorts of straight lines, but they would not fit that definition, the geometry definition. But that's fine, because this is how we use it, and this is how engineers use straight lines to put up buildings, etc. So here we are. Let's try and get a practical definition of probability. And what we're going to do is we're going to take advantage of that long-range stability. If an experiment is repeated n times, I haven't told you what n is, but that's okay. So if an experiment is repeated n times under essentially identical conditions, so we're going to repeat the same experiment, like flipping a coin over and over. We do it over and over. Okay. Essentially identical condition. Now, think of an event A, whatever you want it to be. And suppose this event A occurs m times. So you're doing this n times, and now you're worried about the event A occurring m times. Then, as n gets large, look at the ratio, or the proportion, m over n. This approaches the probability of A. There it is. There is the definition of the probability of A. For large n, it's the proportion of times your event happens. It's as simple as that. And we've seen this. We saw this with the mortality tables. We've seen this repeatedly. Except we just didn't call it probability. But we could have. We called it proportions. That's fine. But this is deliberately vague, because we're trying to, in certain spots, because we're trying to get a practical definition. So I haven't said to you, what is essentially identical conditions? What do we mean by that? Do we need to have the humidity exactly the same? Do we need to have the wind directions exactly the same? And then, what do we mean by n gets large? Is 3 large? Is 3 million large? I haven't said anything. And what do we mean by approaches? Is this in a limit, as in mathematics? Okay, so it's deliberately vague so that we can apply it. You know, something like this, getting back to the essentially identical conditions, we're going to be talking about people. And we're going to say, well, the probability that this patient will survive the operation is 0.4. Why? Because 40% of previous patients have survived that. But are those patients identical? No, they're not. That is how we're going to be applying this, though. So we have to be prepared to understand when we can apply these conditions and when not. But for the time being, let's just go with this. So the probability of the event A is the proportion when n is large. Now, there is a related quantity. There is a related quantity, and that is the odds of A. So rather than the probability of A, we can also talk about the odds of A. And the only difference is that the odds of A, it's also a ratio, but it's the ratio of the number of times A occurred to the number of times A did not occur. And it's interesting because Cardano wrote his whole book was talking about odds, whereas now you hear about odds on the racetrack or in this course when we get to case control studies, etc. But by and large, people tend to prefer probability. If you got the one, you can get the other. It's trivial. There it is on the screen. You can this is just the P of A over 1 minus P of A. So if you've got the one, you can solve for the other. Okay, so it's not like one is different from the other. Okay, we'll come back to odds later. Let's turn our attention back to probability. Just before the Second World War, this fellow by the name of Kerridge was visiting Copenhagen in Denmark, and the Germans invaded Copenhagen, and Kerridge was South African, and so he was interred by the Germans. So here he was imprisoned, and he had nothing to do. So he's a mathematician. What does a mathematician do? Well, he started flipping a coin. So he flipped the coin, and he collected pieces of paper so he could keep tabs of what happened when he flipped the coin. And he had enough paper to note what happened when he flipped the coin 10,000 times. So here are the results of his 10,000 tosses. So you can see that initially it's unpredictable and things go all over the place. But as time progressed, it stabilized. I think this is it's almost at a half, but you know, it's his coin and he's flipping it, so it's not going to be a half exactly. I think it was 0.5067 or something like that, but very close to a half. Okay, so you see that after a while things stabilized, and he wrote a book about this, and it's fascinating. But there you see probability in action. So let's look at a few particular cases of probability. So something must happen. So every time you do this, something happens. So that's of the n times you do it, n times something happens. So the probability of a sure thing is 1. On the other hand, the other extreme, if it's impossible, it never happens. So 0 out of n. So the probability of an impossible event is 0. And in fact, these two define the limits. And in fact, every probability, the probability of any event is going to be between 0 and 1. Remember the complement? Well, if A happened m times, that means the other n minus m times A didn't happen, which is the complement. So the complement is n minus m. So there it is. The probability of the complement is 1 minus the probability of the event. Or another way of saying that is the probability of A plus the probability of A complement is equal to 1. So here we have it in our Venn diagram. M times it happened out of the n. S was n. M is A happens m times. And there's the complement, is n minus n. So we can get that formula from the Venn diagram. It's very nice. What about mutually exclusive events? We spoke about mutually exclusive events, remember? Then if A and B are mutually exclusive events, that means they cannot happen at the same time. That means that the probability of A plus the probability of B is the probability of A union B. Because the probability that A happened or B happened is just going to be probability of A or the probability of B. And we see this in our Venn diagram. There's the Venn diagram for mutually exclusive. So A happened m times, B happened k times of the n. So if they're mutually exclusive, then A or B happened m plus k over n. And so we've got that formula for mutually exclusive events. We give it a name, and it's called the additive law. So the additive law of probability tells us that if we've got mutually exclusive events, now I showed you for 2 of them, but this goes on for any number of them. If they are mutually exclusive, then the probability of the union is the sum of the probabilities. So going to our Venn diagram, there it is. There's no overlap with any of these. They're all bubbles like that, all separated in the Venn diagram. And Venn diagram and probability it's very easy to think of the probability when applied to a Venn diagram as an area. Think of how the areas work and you won't go wrong. So for example, the area of A is the probability of A. And so A and B would be these two together. And so the area of A plus the area of B is the probability of A union B, plus the probability of C plus the area of C. So there's no double dipping. Whereas if A and B are not mutually exclusive, then there is some overlap. And in fact, if we look at the area of A and add it to the area of B and think that that should be the probability of A union B, we'd be wrong. Why? Because we would be bringing this part here, which is A and B, we would be bringing that part in twice. So this would be A intersect B. We would be bringing that in twice if we do our area analogy, and so that would be wrong. So the general formula is the probability of A union B is the probability of A plus the probability of B minus the probability of A and B. Okay, so now you have the additive law.